Welcome to the Great Race, featuring the greedy rabbit and a tortoise. To my left, we have the greedy rabbit, which is enthusiastic but impatient using a greedy algorithm. To my right, we have the tortoise, which is calm and methodical using the A-star search algorithm. Introducing the hype man, the brains behind the competition. And now the tortoise. Go.
Wait, there are too many directions. Which direction am I supposed to be going in?
This is the shortest path with the least heuristic value, h of n. So take this one.
Come on.
Damn, can I eat this? I don't think so. You have a race to focus on.
But I'm a tortoise.
Nah.
There are two paths.
Where should I go? I guess you should be choosing this, as it considers both g of n and h of n value. Despite them choosing that, you should be choosing this. Go ahead.
Wait, there is a path over here and there is a path over here. Where are we supposed to go?
This is the shortest path. Let's take this one.
Should we take a break? It has been so much.
Why not?
Come on, let's swing.
I'll just remind you of something. This is having fun. Don't get distracted. Consider the shortest path. G of n plus h of n. This is the shortest path. Come, let's go.
Did I just lose the match? How can a tortoise win over me? Why did I trust the greedy algorithm? Oh god, I never should have trusted you. I never should trusted the greedy algorithm. Oh god.
So the winner is the tortoise using the A-star search algorithm. But this was just the trailer. Let us look at what really is the A-star search algorithm.
Greetings everyone. I am Keshav Sahu, IPM 05035,
And I'm Arnish SA, IPM 05013.
and together we'll be presenting on the
A-star
A-star search
search
algorithm.
algorithm.
Well, Anish, what exactly are search algorithms?
I got it. So search algorithms are tools in computer science designed to find the optimal solution in any data structure. Linear search and binary search takes care of data in list, whereas optimization algorithms like A-star algorithm and greedy first algorithm takes care of data which are a little bit complex and gives us the optimal solution. So you may ask, what is a A-star search algorithm?
A-star search algorithms are graph traversal and path finding algorithms used to find the shortest distance between two nodes in a weighted graph. It's said to be the combination of the greedy best first search algorithm and the Dijkstra's algorithm, which makes it optimal for AI, game building, and robotics.
Now we look at the similarities between A-star search algorithm and greedy best search algorithm. Both A-star search and greedy best first search uses heuristic to guide their search, but A-star also incorporates the cost to reach the current node, while greedy best first search only considers the heuristic. Greedy best first search prioritizes nodes based on the heuristic value hn alone. It aims to explore the most prioritizing nodes first using hn to estimate the distance to the goal. So if you look at this example, starting at point A, the algorithm chooses to go to C because of its heuristic value, which is 25, which is less than the other two heuristic values. And then from C, it chooses to go to F and not E because the heuristic value to reach F is less than what it is to reach E. And then from F, it reaches G, and it's the only path.
Now let's see how Dijkstra's algorithm and A-star are related. Dijkstra's helps us to find the shortest distance from the start node to all the other node. It only takes into consideration the actual cost, means it ignores the heuristics. We can say that Dijkstra's algorithm is A-star algorithm when heuristics is 0. Dijkstra's is fast, but it is not as reliable as A-star algorithm. Thank you.
Hello everyone, I am Bukya Karthik, IPM 05019. Now let's try to understand the heuristic functions and their role in the A-star search algorithm. This is a popular algorithm which is used to find the shortest distance, as Arnesh and Keshav has introduced. These functions provide an estimate of the cost to reach the goal from a given node, helping A-star efficiently explore the search space and find the optimal solution. Now let's try to understand how this actually works. Estimate cost. The heuristic function provides a lower bound on the remaining cost to reach the goal from a given node. Prioritize exploration. A-star uses the heuristic to prioritize nodes for exploration, focusing on that seem most likely to lead the goal quickly. Efficiency. A well-chosen heuristic can significantly reduce the number of nodes explored. That is, making the A-star more efficient than algorithm like Dijkstra's algorithm. Thank you.
Good morning, I am Mudit Mohan, IPM 05043. So now we'll talk about the types of heuristic functions. There are mainly two types of heuristic functions, which is admissible heuristic. A heuristic is called admissible if its never guesses too high. This makes sure that A-star will always find the best and cheapest path to the goal. The second is consistent heuristic. If a heuristic is consistent, it ensures that A-star doesn't have to revisit nodes, which save time. There are two more types of heuristics, which are informed heuristics and uninformed heuristics. The informed heuristics are these use special knowledge about the problem. For example, in map-based pathfinding, the straight line distance is a common heuristic, and uninformed heuristics, these don't use any special information like in uniform cost search, where the algorithm explores path based on the actual cost so far. Thank you.
Hello, this is Pendyala Sohan Chiranjeevi, IPM 05049. Now let's look at a practical example of A-star search using this map of Romania. Here is the geographical map of Romania, where we designed this path from different cities to find out the distance, shortest distance between Ered to Bucharest using the A-star search. So moving ahead. So as you can see, we have set up the map as follows. So what exactly is A-star search? A-star search is f of n is equal to g of n plus h of n, where g of n is the actual path's cost so far from the start node to the current node, which are the weighted edges here from one city to another city, like the 75 and 118 here. And for h of n is the actual straight line distance between the different cities on the map to the end goal, which is Bucharest here, which is given by the table here. So in that way, we'll be calculating the A-star search, which will be further explained by Vedant, where we'll be showing how we'll move from the start point Ered to the end point Bucharest.
Hello, I'm Vishwanath Vedant, IPM 05069. So firstly, we'll be starting with Ered. Here, the h of n value of Ered is 366 and g of n value is 0, as it is the starting point. So Ered has three cities connected to it, which is Sibiu, Timisoara and Zerin. Here, h of n plus g of n value of Sibiu is 393 and it is the least value, so we'll be choosing Sibiu. So further, Sibiu is connected with 4 cities, and here Rymnicu has the least value, so we'll be choosing with Rymnicu. So Rymnicu is furtherly connected with 3 cities, and Petesti has the least value. This could be another scenario. As we can see, Petesti has the least value of 417, and we finally reached to Bucharest, which is the desired destination.
So that is how we found out the shortest distance between Ered to Bucharest being 418 in the A-star search algorithm, considering both the actual cost and heuristic cost. But let us also look at the greedy search method for calculating the distance, which only considers the heuristic cost. In this case itself, considering the distance between Ered to Bucharest using the heuristic cost only, the distance comes out to be 450, which is way greater than the 418. So in this case, we can see the A-star search is better. So like these cases, we can see the A-star search is much better than the greedy search. So the A-star search is a combination of both the Dijkstra's and the greedy search method, which gives us optimal values. Moving ahead, I'll be passing on to Vedant, who will explain the algorithm code for this.
So this slide provides the overview of the entire pseudocode of A-star search in the Romanian map. Let us discuss it briefly. We initialize with two lists, the open list and the closed list. We begin with the start node Ered, set as g of n is equals to 0, and we calculate f of n is equals to g of n plus h of n, as we did earlier. We use a loop where, while the open list isn't empty, it selects the node with the lowest f of n. If it reaches the final goal, which is Bucharest in this case, it stops and reconstructs the path. For each neighboring city, we calculate G neighbor and F neighbor. Here, the neighbors are the cities. We add the neighboring cities in the open list if they offer a better path. Finally, we reconstruct them. When the goal is reached, we trace back through the parent nodes to get the path. Thank you.
Now let's compare the strengths and weaknesses of these algorithms.
First, we look at the A-star search algorithm. It balances speed and accuracy with heuristics.
However, it needs a good heuristic to be efficient.
It is optimal and complete.
Moreover, it is space intensive in nature. Moving on to the Dijkstra's algorithm.
It guarantees the shortest path.
However, it is slower than A-star for large graphs.
It does not require a heuristic, making it useful for all weighted graphs.
However, it explores all the nodes regardless of the proximity, making it inefficient for large cases. Now moving on to the Prim's algorithm.
It finds the minimum spanning tree.
However, it's not useful for finding the shortest paths.
It is efficient for dense graphs.
However, it is slower for sparse graphs without optimization, like using a priority queue. Moving on to the Bellman-Ford algorithm.
It handles graphs with negative edge weights.
However, it is slower than the Dijkstra's algorithm.
It guarantees the shortest path even with negative weights.
Moreover, it cannot handle negative weight cycles if a negative cycle exists.
Okay, so now we have understood about heuristic roles in A-star search. So let's try to understand its real-life applications. The first step is robotics, robot navigation. A-star is wisely used in autonomous robots to plan the most efficient route in 2D and 3D space. That is, robots such as vacuum cleaners or drones use A-star to move optimally from one location to the another. And the next step is network routing. That is optimal data routing. A-star can be used to find the most shortest path in the computer networks, that is optimizing data transmission by choosing the fastest route through network nodes, ensuring lower latency and faster data transfer. The next step is GPS, navigation systems. That is, we use it in our everyday life to travel from one place to the other place. A-star is fundamental algorithm that helps optimize routes based on factors like distance, traffic and time. Few more applications will be explained by Mudit.
So far we have seen some of the real life applications. Now we'll understand the structure, how the A-star algorithm actually works, and we'll use A-star algorithm in robot vacuum cleaners like iRobot's Roomba. So first step is efficient coverage. A-star helps the vacuum to find the most optimal route to clean a room or floor path. It ensures the robot covers the entire area without unnecessary retracting or missing spots. Second step is obstacle avoidance. By using real-time data from sensors, A-star allows the vacuum to dynamically adjust its path when it encourages objects like furniture, pets or toys. It regulates the shortest path around obstacle and continue cleaning efficiently. Third is battery optimization. The algorithm helps the vacuum optimize the movement to reduce the amount of energy it spends traveling between different areas. The last step is docking and recharging. When the battery is low, A-star helps the vacuum to find the shortest path back to its charging dock.